Okay, so in this video, we're going to be talking about binomial probability and expected value. So it says, so far we have discussed probability, probability of compound events, and conditional probability. So what we're going to do today is talk about binomial probability. Now, binomial probability, bi means two. So the definition is the probability of getting one of two outcomes. Now, for an example, if you flip a coin, you got two options. You can either land on heads or you can land on tails. It says that if you have a binomial situation, then the probability of the size of the sample space is going to be 2 to the nth power, where n is the number of trials. So if you flip a coin 20 times, the sample space is going to be 2 to the 20th power, which is 1,048,576. That means that you're going to have 1,048,576 number of possible outcomes during the 20 trials. Now it says at the National Baseball Batting Contest, organizers have set up game booths for contestants. Richard wants to win a large stuffed animal, and the rules of the game are as follows. It says you're pitched 5 fastballs, and you must hit them into a fair zone to count. If you hit all 5, you get a large stuffed animal. If you get 3 or 4, you win a small stuffed animal. 1 or 2, you win a bat-shaped pencil, and if you hit none, you get nothing. But it says the game costs $3 to play for each set of 5 fastballs. And it asks us, what are the possible outcomes Richard can have on his 5 swings? So normally you can make a tree diagram, right? You can have, for the first pitch, a hit or a miss. Second pitch, hit or a miss. Third pitch, and on and on and on. So each one of these is going to have a bunch of little graphs on it, right? But that can get really tedious and really, really annoying to organize. So instead of doing that, what we could do is we could just list. Because if you think about it, how many possible branches are we going to have? We're going to have 2, and then we got 5 pitches, so we're going to have 32 branches to count. And that's just going to be annoying, and that's actually not that big of a sample space. Imagine having 40 pitches and having to do it. So instead of doing that, we're going to list all of them. So you list all the possible outcomes. You can have, you can miss all of them. Hit 1 out of 5. Hit 2 out of 5. 3 out of 5. Hit 4 out of 5, or hit all of them. Hit 5 out of 5. Okay? But I want to clarify, these are all options, but order matters. Okay, so depending on the order that you get these in, will determine the total number of outcomes. And we're going to look at an example of that on the next page. So it says using a tree diagram is a very tedious method of listing sample spaces as a size gets larger, like we just talked about. As a sample space becomes very large, we need to rely on more efficient methods to determine what the size of the sample space will be. For this example, we could count the leaves of the tree diagram, or we could use the formula. So the formula is our example with 5 pitches has 2 to the 5th, or 32 outcomes. What is the probability of Richard successfully hitting the following? What if he hits all 5 pitches? Well, if you're going to hit all 5 pitches, remember we said there are 2 outcomes. You can either hit or miss. So to get all 5 pitches, you have to get 5 hits in a row. And that's the only way you can get all 5 pitches, right? Well, that's only 1 out of the 32 possible outcomes. So the probability of getting all 5 hits is 1 out of 32, which is the same thing as 0.031 or 3.1%. Now, if you get 4 pitches, this is where order matters, okay? It didn't really matter with all 5 pitches getting hit because there's only 1 outcome. But whenever you only have 4 hits and 5 total pitches, you could get a hit, then a hit, then a hit, then a hit, then a miss. Or you can get 3 hits, a miss, and a hit, 2 hits, a miss, and 2 hits, a hit, a miss, and then 3 hits. Or you can get a miss and then 4 hits in a row. So all of these have the same outcome, which is 4 hits in 5 pitches, but they're in different orders, right? So in this example, you have 5 possible branches that you could travel to get the same outcome. So 5 out of 32, which is the same thing as 0.156 or 15.6%. Now, even this can be a little bit annoying to do. Having to list out all of these values can get annoying, right? So what we could do is we can actually recruit the help of our graphing calculator to help us do this. And on a graphing calculator, you have a function called Binomial Pdf in PX. And now this function on your calculator is going to help us be able to do this without having to list out all of these outcomes. Now the NPX, the N represents the number of trials. Here, let me get my laser. N is the number of trials, P is the probability of success, and X is the number of successes you want to have. So let me pull up a graphing calculator here. And let's just do a couple examples. So let's say, for example, you wanted to get 5 pitches. You wanted to hit 5 out of 5. Remember, N is the number of trials that you're having. Well, you have 5 pitches being thrown at you, so N is 5. P is a probability of success. So whenever you go up to bat, there's only 2 outcomes. You can either hit it or you can miss it. So you have a 50-50 chance of probability. So our P is going to be 0.5. And then X is the number of successes you want to have. In this case, we want to hit all 5 of them. So X is going to be 5. So on our graphing calculator, you would hit, to get to the Binomial Pdf function right here, you're going to go second VARS, and then you're going to scroll down to option A. Option A is Binomial Pdf. If you hit enter, it's going to ask you for your trials, which is N, P, and then X value. So in this case, our trials is 5, our P value is 0.5, and our X value is 5. If we hit enter and then paste, our function is going to look like that. And I'm going to write it down here. So Binomial Pdf, in parentheses we have 5, 0.5, and 5, which if I hit enter, it's going to tell me that it's equal to 0.031, I'm just going to round it, or 3.1%, which is exactly what we got up here. We got 0.031 or 3.1%. So if I did 4 pitches, well, our N is still 5. We're still getting 5 pitches. Probability is still 0.5, but this time X is going to be 4. So it's going to look like Binomial Pdf 5.54, and that's going to equal, if I do it, second VARS, go down to option A, 5.54, I should get 0.156 or 15.6%. And so I'm just going to go through and do these last 2 on here. So N is 5.5, and then 2 pitches we want to hit. Binomial Pdf 5.52. And so this time we got 0.3125 or 31.25%. And then if I wanted 0 pitches, it's going to be 5, 0.5, and 0. Our function is going to look like Binomial Pdf 5.50, which equals 0.031 or 3.1%. So you have the same probability of getting all 5 pitches as you do 0 pitches. All right, so it says expected value. Now expected value, here, let me hide my calculator real quick. Expected value is an average or weighted value found by multiplying the value of each event by its probability and then finding the sum of its products. In other words, expected value is the average payoff over the long run. Now it says, suppose that Richard tries the game 10 times. So he gets 5 pitches each time, and he's going to try it 10 times. How many times do you expect him to successfully hit the given amounts of times below? So we got 5 hits. All I'm going to be doing is I'm just going to be taking the values we got on this page in our table down here. So right here, 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 and here. And I'm just going to be transferring them over to this page. So we said that the probability of getting all 5 hits, we said that was 1 out of 32. So our expected value, if he does one game, is 1 out of 32. And he does that 10 times, he should get the probability, the number of times he should succeed in getting all 5 hits is 0.3125. So he should get about 0.3 wins over 10 tries. So he's not even going to get all 5 hits in 10 attempts. He can try this game 10 times, and according to the probability, he should not even succeed in getting all 5 hits a single time. He should only get about 0.3 wins. Now, 4 hits. The probability of getting 4 hits, we said, was 5 out of 32, right? So our expected value is 5 out of 32 times 10, which is about 1.56. So he should get somewhere between, I can say I would expect him to win 1 or 2 times over 10 tries. So if he tried this game 5 pitches a time, 10 times, we should expect him to get 4 hits out of the 5, 1 or 2 times in total. Now, if he does 10 hits, we said the probability, 2 hits. Probability of 2 hits, we said, was 5 out of 16. So our expected value is 5 out of 16 times 10, which is the same thing as 3.125. So I would expect him to win 3 times over 10 tries. So if he goes up and tries this game 10 times, we should see him get 2 hits about 3 out of those 10 attempts. And then the probability of 0 hits, we said again was 1 out of 32. So our expected value is 1 out of 32 times 10, or 0.3125. So I'm just going to say don't expect him to win it all. So we should not see him get 0 hits out of 10 tries. Now, it says that everyone has the same chance as Richard to win. If 160 people each play the game once, how many large stuffed animals will be won? So in order to get a large stuffed animal, they have to get all 5 hits, right? So the probability of 5 hits, we said, was 1 out of 32. Now, we have 160 people going. So our expected value is 1 out of 32 times 160, which is the same thing as 160 over 32, or let me get my calculator real quick. 160 divided by 32 is 5. So I expect to give out 5 large stuffed animals. Now, if 160 people each play the game once, how many small stuffed animals will be won? So in order to get a small stuffed animal, you have to get 3 or 4 hits. Okay? So the probability of getting 3 hits is 5 out of 16. Probability of 4 hits is 5 out of 32. So our expected value, actually, before we go to expected value, I need to look at the combination of those two, okay? So probability of 3 or 4 hits. So that would be 5 out of 16 plus 5 out of 32, which is the same thing as 15 out of 32, or 0.46875. So our expected value, remember, it's going to be 0.46875 times the 160 people. Okay, so that should equal about 75 small stuffed animals. And then the last question, it says if 160 people each play the game once, how many bat-shaped pencils will be won? So this is the same process as before, only with probability of 1 or 2 hits. So the probability of 1 hit is 5 out of 32. Probability of 2 hits is 5 out of 16. So the probability of 1 or 2 hits is 5 out of 32 plus 5 out of 16 for a total of 15 out of 32, or 0.46875. So my expected value, remember we have 160 people, so 0.46875 times 160 is going to be equal to 75 bat pencils. So we have the same probability as question 5.